In this question, we have a reaction with an activation energy of 16.5 kilojoules per mole. It's carried out at 287 Kelvin. Our goal is to figure out the activation energy in the given units of joules per mole, to figure out what fraction of collisions are effective, and to figure out for every 1 million collisions that happen, how many are effective. So those are our goals. Let's head to our reference sheet and find a relevant equation for this. So up here we have the Arrhenius equation. And this equation tells us the fraction of successful collisions based on our activation energy, R, where R is the molar gas constant, and T, which is the temperature. So let's go ahead and write down our equation. So the F in our equation, that's the fraction of successful collisions or effective collisions. So that's what we're trying to find here. We've got E, which is just the number in math. We've got capital E with a little a next to it. That's our activation energy, which we're given here in our question. We've got R, which is the molar gas constant, reminding ourselves from our reference sheet. R is 8.31 joules per Kelvin mole. And then we have T, temperature, which is 287 Kelvin from the question. So you'll notice that R is in units of joules per Kelvin mole. So that means that our activation energy is going to need to be in units of joules per mole, as asked in that first question. And our temperature is going to need to be in units of Kelvin, as given in the question, since R has joules per Kelvin mole as the units. So that's why our first step is going to be converting our activation energy from kilojoules per mole into joules per mole. So let's do that first. So we have 16.5 kilojoules per mole, and we want to convert that into just joules per mole. So I'm going to use dimensional analysis for this. So I need to change kilojoules into joules. So I'm going to put kilojoules on the bottom so they'll cancel with my kilojoules in my unit. And then I want joules on the top. And to convert from kilojoules into joules, kilo means 1,000. So 1 kilojoule is equal to 1,000 joules. So that's my conversion factor that I'm using here. So 1 kilojoule is 1,000 joules. Okay, so we're going to multiply everything on the top, multiply everything on the bottom, cancel any units that are the same on the top and the bottom. So the kilojoules cancel. We're going to be left with joules on the top and moles on the bottom, joules per mole, which is what we want. So putting that in our calculator, we're doing 16.5 multiplied by 1,000 joules divided by 1 multiplied by moles. So 16.5 times 1,000, when we put that in our calculator, we get 16,500 joules per mole. So that's our first step, finding our activation energy in joules per mole, 16,500. So now we've got everything in the right units because we've got joules per mole for activation energy, Kelvin for temperature, and joules per Kelvin mole for R. We're ready to put those things into our equation to find the fraction of effective collisions. So let's go ahead and do that. So we've got E to the negative activation energy in joules per mole, which is 16,500, divided by RT. So R, that's our gas constant, 8.31. Multiplied by the temperature in Kelvin, which is 287 Kelvin. So we're going to put that all into our calculator, and that gets us a value for the fraction of effective collisions of 0.000989. So that's our fraction of effective collisions. So let's go ahead and fill that in this box here, 0.000989. Awesome, okay. So that's our fraction of effective collisions. Now, to make some meaning out of that, we're going to figure out if we had 1 million collisions that happen, how many of those would be effective? To do that, all we need to do is take our fraction and multiply it by 1 million. So our fraction is 0.000989, and I'm going to multiply that by 1 million. 1 million is a 1 with 6 zeros, or in other words, 10 to the power of 6. So if we calculate that out, I end up getting 989. So that's my answer. I'm going to fill that in here to check it's correct. So what that means is that for every 1 million collisions that happen, 989 of them are effective. Let's try one more question of this type. So in this question, we're told the temperature is 297 Kelvin. And we're told that 1,660 in every 1 million collisions are effective. So this time we're given the effectiveness and we have to work backwards to figure out the activation energy in both of those units. So let's just identify which variables we have. The activation energy, that's what we're trying to find. R, that's our molar gas constant. Remember, we're given that. It's 8.31 joules per Kelvin mole. It's the same every time. The temperature T, we're given that here. It's 297 Kelvin. F, the fraction of effective collisions, we're going to have to figure that out from our description of 1,660 in every 1 million collisions being effective. So let's do that first. So if we have 1,660 in 1 million, that's going to be our fraction. So if we put that into our calculator, we're going to end up getting 0.00166 as our fraction of effective collisions. So let's check that in our answer box. Awesome. So that's our fraction of effective collisions. So there's our F. Now we have enough information to go ahead and use our equation to find the activation energy. However, we need to rearrange it to find the activation energy. Right now, we have e to the power of negative activation energy divided by RT. In order to get rid of the e to the power of, we're going to have to take the natural logarithm, ln, of both sides. So let's do that now. So we're going to have ln of F, and we're going to have ln of e to the negative activation energy divided by RT. And ln is the inverse function of the exponent e to the power of. So those kind of cancel out, and we're left with ln of F is equal to negative activation energy divided by RT. So we're trying to find the activation energy. Right now it's divided by RT. So let's multiply by RT on both sides. That means the RTs are going to cancel out on the right. And we're left with negative EA on the right and RT multiplied by ln F on the left. Finally, we want to get rid of that negative sign. So I'm going to multiply both sides by -1. And I'm going to end up with the activation energy is equal to negative RT ln F. So that's how we rearrange our equation to find activation energy. So now we can go ahead and put in our numbers. We've got negative R. Remember, R is a constant, 8.31, multiplied by T, the temperature in Kelvin, which is 297, multiplied by the natural logarithm, ln, of F, the fraction of effective collisions, which we already calculated was 0.00166. So we put that all into our calculator. That gets us 15798 joules per mole. That's our activation energy, 15,798 joules per mole. So we can go and fill that in here in our first box. The reason why it came out in units of joules per mole is because R, the gas constant, is measured in joules per Kelvin mole. So that's why we ended up with joules per mole. However, if we also want to find our answer in kilojoules per mole, we're going to have to do a conversion now. So I'm going to set that up here. We've got 15,798 joules per mole. So I'm going to set this up as a conversion with dimensional analysis. And I want to change the joules into kilojoules. So I'm going to put joules on the bottom so it will cancel out. Kilojoules on the top. And remember, 1 kilojoule is 1,000 joules. Here's that conversion factor that we're using. So I'm going to put 1 kilojoule on the top and 1,000 joules on the bottom. The joules are going to cancel out. And we're left with 15,798 multiplied by 1 kilojoule. And on the bottom, we have moles multiplied by 1,000. So our unit we're left with is kilojoules per mole. And to calculate that, it's going to be 15,798 multiplied by 1 divided by 1,000 kilojoules per mole. So if we put that into our calculator, we're going to end up getting 15.798 kilojoules per mole. So we can go ahead and fill that in our last box over here. Awesome. So on this question, we're using that same equation, the Arrhenius equation. However, we needed to rearrange it for our activation energy. So we needed to use the natural logarithm, which is the inverse function of the exponent e to the power of, and rearrange that to get our activation energy. We needed to first find the fraction of collisions based on how many in 1 million were effective. And remember, R is in joules per Kelvin mole, which means the activation energy we calculated was in joules per mole. So to get our final activation energy in kilojoules per mole, we then had to do a conversion. So there's quite a few steps here. Just make sure that before you use this equation, everything's in units of joules, moles, and Kelvin, and that F is our fraction of collisions that are effective.